Okay, folks. So the plan for this week is, number one, we are going to finish up our discussion of thermodynamics, specifically Gibbs free energy today. We will be talking about Gibbs free energy under non-standard conditions. If time permits, I would like to at least introduce balancing redox reactions. And then tomorrow in lab, be prepared to take notes the first hour and a half of lab. I will be going over Gibbs free, I'll be going over balancing redox reactions. We will get into the galvanic cell, and most likely we will get into standard potential energy. And then Wednesday, your thermodynamics lab from last week is due. We will probably get close, if not finishing, the electrochemistry lab on Wednesday. And then Friday I will meet. I should, if all goes well, have your test written for the following Monday, not Monday of Thanksgiving week, but the Monday after. And we'll give you insight into that. And we will, and also the electrochemistry lab will be due that day. Okay, any questions before I get started? Yes. No pre-lab. Other questions? Okay, then I'm going to go ahead and get started. We've been talking about Gibbs free energy under standard conditions, and Gibbs free energy can be calculated in a couple of different ways. The naught represents that it's under standard conditions, which is typically 1 molar for a solution and 1 atmosphere for a pressure. Gibbs free energy can be calculated as the delta G naught is equal to the delta H of the reaction minus T delta S for the reaction. We can also relate Gibbs free energy, which tells us whether a reaction will occur, meaning is it going to occur in the direction it is written, with the equilibrium constant. And that equation is delta G naught is equal to negative RT natural log of K. Now, where K is equal to the equilibrium constant. Now, let's talk about Gibbs free energy under non-standard conditions. Under non-standard conditions, we calculate Gibbs free energy as delta G under non-standard conditions is equal to the delta G naught under standard conditions plus RT natural log of Q. And Q goes back to our early discussions of equilibrium when we talked about the reaction quotient. Q is calculated the exact same way that K is calculated. It's just Q is assuming that the reaction is not at equilibrium, whereas K means it's at equilibrium. So let's just look at Gibbs free energy under non-standard conditions. So calculate delta G when, or let's say, let me back up, calculate delta G for 2NH3 gas goes to form N2 gas plus 3H2 gas when the concentration of N2 is equal to 0.01 molar. The concentration of H2 is equal to 0.01 molar. And the concentration of NH3 is equal to 0.1 molar. The enthalpy of reaction under standard conditions for this reaction is 92.4 kilojoules. And the delta S of reaction under standard conditions is equal to 198 joules per Kelvin. Okay, so in order to get this, we need to obtain all of the factors involved in this equation. The first factor that you need in this equation is delta G naught. So delta G naught is equal to delta H naught minus T delta S naught. We've been told that the delta G is 92.4 kilojoules minus the temperature. We're going to assume it's 298 Kelvin unless told otherwise. Times our delta S naught, which is a positive 0.198 kilojoules per Kelvin. As a reminder, since we have slept over the weekend, you have to make your units match. So when you calculate your delta G naught, you get a delta G naught of 33.396 kilojoules. Questions? Yes.
33.396. Why do you not round that to 33.4 sig figs?
If I am worried about sig figs, I would be rounding it to 33.4. But I tend to keep most of my digits until the very end, even when I am trying to do significant digits. Now, the next thing we need is our R value. Our R is 8.314 joules per mole Kelvin. Right off the bat, I see that I'm going to have my Gibbs free energy in joules to make my units match. So that means it's going to be 33,396 joules. My T is 298 Kelvin. And the other thing I need to calculate is I need to calculate Q. Q is going to be the products over the reactants. So it's going to be into raised to the power of 1 times H2 cubed divided by NH3 squared. So the Q is going to equal 0.01 times 0.01 cubed divided by 0.1 squared. When you key this into the calculator, you get a value of 1 times 10 to the minus 6 for our Q value. Now that we have all of the pieces, we can do the calculation. Gibbs free energy under non-standard conditions is equal to Gibbs free energy under standard conditions. Plus RT, that's 8.314 joules per mole Kelvin, times 298 Kelvin, times the natural log of Q, which is 1 times 10 to the minus 6. When you key that into the calculator, you get to delta G of a negative 832.9 joules, or negative 0.833 kilojoules. What this tells me, folks, is while the reaction of the decomposition of ammonia is not favorable under standard conditions, if we alter the concentration of the reactants and alter the concentration of the products, we can drive that reaction so that it will occur naturally. Questions? Okay, let's look at one more example. It's not going to get any tougher than that. You want to know the most common mistake? people get in a hurry and they don't write out their Q expression, and they wind up forgetting to square and cube where appropriate in this type of reaction. That's actually where they get into the most trouble. Okay. Two N2O gas plus 3 O2 gas goes to make 4 NO2 gas. The delta H naught for this reaction is a negative 31.6 kilojoules. So it is favorable with respect to enthalpy. And it has a delta S naught equal to negative 98 joules per Kelvin. So it is not favorable with respect to entropy. What is delta G when the concentration of NO2 is 1 molar, the concentration of O2 is 0.50 molar, and the concentration of N2O is 0.50 molar. At 298 Kelvin. I'm going to give you time to work through this problem. Okay, let's see how it's going. First thing you had to do is calculate delta G naught and Q. The reason we did that is because we suspect it's under non-standard conditions because the concentrations are not at 1. The concentrations don't even come out to be, this number doesn't come out to be 1. So it's not at equilibrium. Basically, anytime there's concentrations involved, suspect it's under non-standard conditions. You got to prove it, but you can suspect it's under non-standard conditions. So I calculated delta G naught. That's a negative 31.6 kilojoules minus 298 Kelvin times a negative 0.098 kilojoules per Kelvin. Make sure your units match. When you do so, you get a negative 2.396 kilojoules, meaning that this reaction under standard conditions is favorable. However, because we're not certain if it's under standard conditions or not, we have to calculate it, and we've got to assume it's under non-standard conditions. So we start by calculating Q. Q will be equal to NO2 to the 4th divided by N2O squared times O2's cubed, or 1 to the 4th divided by 0.5 squared times 0.5 cubed, which gives you a value of 32 for Q. You then plug that into your Gibbs free energy equation for non-standard conditions, and again, making sure all your units match. So it's a negative 2,396 joules plus 8.314 joules per mole Kelvin times 298 Kelvin times the natural log of 32. And you get a delta G of 6,190.6 joules, or positive 6.19 kilojoules. So under these conditions, this reaction is not going to occur without some external influence, such as a change of temperature, where it did occur under standard conditions. Questions? Hardest part, making your units match. Second hardest part is remembering how to calculate Q. Otherwise, these equations, folks, if you do those two things, they're plug and chug equations. Then it's just a matter of understanding what they are saying to you. Is it favorable or is it unfavorable? Okay. That finishes the thermodynamics chapter. And now we move on to the last chapter of the semester. Which is electrochemistry. Okay, so you learned in College Chemistry 1 that several types of reactions involve a transfer of electrons. Some of those include single displacement reactions, combustion reactions, and some synthesis and decomposition reactions. Basically, in College Chemistry 1, to these reactions, you would wind up applying oxidation numbers and watching as the oxidation numbers change from reactant side to product side for certain elements. That change in oxidation number meant that there was a transfer of electrons, and a transfer of electrons is what electrochemistry is all about. It's the flow of electrons associated with electricity. Now, the first thing we're going to discuss in electrochemistry is we are going to balance redox reactions. And I hate to say it because I know that it gets groans. Balancing redox reactions is not the same as balancing reactions. When you balanced reactions in college chemistry 1 and even here and there in this course, the main thing you focused on was to make sure that the number of atoms on the reactant side of an element equaled the same number of atoms on the product side of that element. In other words, you were balancing by mass, because mass couldn't be created nor could it be destroyed. When you start getting into redox reactions, you not only have to balance by mass, but you also have to balance by charge. And so it's a mass and charge balance process. Now, the simplest method to do balancing redox reactions is to use half reactions. So, and these steps are going to be slightly different than they were online, but only slightly. The first thing we're going to do is we're going to break down the overall reaction into 2 half reactions. One for oxidation and one for reduction. Folks, this step can be done according to the type of element, the element's identity. Then we have to know the environment that it's in. We're going to next balance the reaction with respect to mass. But to do so, you have to know if it's an acidic reaction or a basic reaction. For an acidic reaction, you're going to start by balancing all elements except hydrogen and oxygen. You will then balance the oxygen by adding water. And finally, we will balance the hydrogen from the water and other compounds by adding H+. There's where the acidic comes into play. For a basic reaction, start by doing the same thing as for an acidic reaction. But then you add OH minus to the same side of the equation as H plus to neutralize the H plus. I'm mainly giving you this the basic reaction in case you encounter it at any time, but I don't expect to give it to you. I expect to focus on the acidic reactions. Step 3 is then to balance each half reaction with respect to charge by adding electrons. The next step is that we are going to make the number of electrons in both half reactions equal by multiplying the half reaction by the appropriate coefficient. Finally, you are going to add the half reactions back together and cancel species that appear on both sides of the equation. Okay. I think the best way to do this is to see some in action. As always. We're going to start with a simple one, and I'll probably pick up with a couple of more complex ones tomorrow in lab. But given the time and walking through each step, I want to just start with a simple one. So the equation we're going to look at is potassium solid plus chromium 3 plus aqueous goes to form chromium solid plus potassium aqueous. This one's actually going to be fairly easy, but we're still going to do it by the steps. Step number 1, we're going to break this equation down into 2 half reactions. You're going to basically keep the elements that are the same element together. So our potassium solid is going to react to form potassium ion. And our chromium 3 plus ion is going to react to form chromium solid. Now, I forgot to mention that this is in an acidic solution. So the first thing we would do is we would look and see, are there any oxygens? Well, no, excuse me. The first thing we would do is balance the element itself. In our our left hand reaction, there is 1 potassium on the reactant side, there is 1 potassium on the product side. It's balanced. On the right hand one, there is 1 chromium on the reactant side, there is 1 chromium on the product side. It's balanced. So then we look at this under acidic conditions. Is there any oxygens? No. So we don't need to add water, which means we don't need to add H+. So our next step, we are up to step number 4, and that is to make the electrons match. Or no, I'm sorry. Step number 3, balance the half reactions with respect to electrons and charge. So right now, on the left-hand side, potassium in its natural state has a charge of 0, and we have a charge of +1. The only way you can make charges equivalent is by adding electrons. And an electron carries with it a negative charge, so it's always going to be added to the side that has the greatest plus. So we're going to add an electron to the right-hand side of the left equation. Because by doing so, now the 2 sides are equivalent with respect to charge. For our right-hand equation, again, we have to make our charges equal. On the right-hand equation, the chromium solid is 0 charge, but the chromium ion is a +3. Again, the only way you can do this is by adding electrons, which are negative. The negative always has to go on the side with the positive. So we're going to add 3 electrons because then we have a -3 +3, and that does equal 0. Now we're up to step 4. Step 4 says to make the number of electrons in both half reactions the same. To make the number of electrons in both half reactions the same, we have to multiply this left half reaction by 3. Then we'll get 3 potassium solid goes to make 3 potassium ion plus 3 electrons. Step number 5 says to add the half reactions back together. So on the reactant side, we have 3 potassium of the first equation. Of the second equation, we have 3 electrons, and we have a chromium 3+. On the product side of the left-hand equation, we have 3 potassium ions. We have 3 electrons. And on the right-hand side of the right-hand equation, we have 1 chromium. You cancel out anything that appears on both sides of the equation, which will be your electrons. And so the balanced reaction, the balanced redox reaction is 3 potassium plus chromium 3+ goes to form 3 potassium ions plus chromium. You should always do a check to make sure that the number of elements is the same and to make sure that the charge is the same. And what I see is I have, if I list this out, I have potassium, chromium, and charge. On the left-hand side, I have 3 potassium, 1 chromium, and the overall charge is a +3. On the right-hand side, I have 3 potassium, 1 chromium, and the overall charge is a +3. So this is a balanced redox reaction. Do me a favor before tomorrow. I'm going to let you out 6 minutes or 5 minutes early. Review the steps. Get them down in your head, because what we're going to do is we're going to start with balancing tougher redox reactions where we'll actually have to worry about the waters and the hydrogens and the electrons. We will, from those redox reactions, we're going to talk about who is oxidized and who is reduced, because that is going to be directly related to the galvanic cell, where you put the oxidized half reaction in the anode and the reduction half reaction in the cathode. And that's also going to play into our redox potential. So please take time and review it so that you're ready for talking about redox reactions tomorrow and galvanic cells. I will see you tomorrow for lab.